Hey everybody, I'm Beej with Lambda School, and today we'll be talking about graphs and one of the more famous algorithms involving graphs called a breadth-first search. And we'll be talking about some of the uses of this and stepping through an example or two to see how they work. So a breadth-first search is a search across a graph that starts with one node and then spreads out evenly to all the vertexes away from that node in a breadth-first manner, as opposed to a depth-first search, which would start with one vertex, dive deep across the graph to another one, and then back up and dive deep across the graph to another one, and so on. The breadth-first search is far more regular, searching in sort of an onion skin layer by layer outward with the next closest vertexes as it goes. And we'll demonstrate this in a little bit. What are some of the uses of this? Well, there are plenty of uses, and we'll try to demonstrate a few of them in our live example. But we've got uses like pathfinding and routing. You can find neighbor nodes in a peer-to-peer network like BitTorrent. Web crawlers use this kind of search to search through connections from web pages. Finding people and connections away on a social site, you can also do this kind of thing. If you want to find neighboring locations on a graph, or if you want to broadcast in a network, or if you want to detect cycles or connected components in a graph, breadth-first search can help with all of these, as well as solving a number of theoretical graph problems. Now, I mentioned connected components, and this is something we'll be looking at more later. Here's an example of connected components. This graph has 3 connected components. There's one up here, this group of 4 verts. There's this big group in the middle, and this other group at the bottom. Each of these groups is a connected component, and using breadth-first search can help find these connected components. And so what is breadth-first search? Here's an example of a breadth-first search running. It starts with node 6, which it colors gray, and then colors all of 6's neighbors gray. And then we're done with 6. And we color all of 4's neighbors gray, and then we're done with 4. And then we color all of 3's neighbors gray, and then we're done with 3, and all of 5's neighbors we color gray, and then we're done with 5. White, 2 has no more neighbors that were still white, so it gets colored black, and so does 1. And if you notice the way this progresses, it progresses from the left-hand side over to the right-hand side in a very smooth manner. We don't dive straight from 6 to 1 and then 6 to 2. We move slowly and deliberately across the face of the graph in a breadth-first manner. So how does this algorithm actually work? Let's give a shot of going through it, and we'll also build a breadth-first tree while we're doing it and try to detect a cycle while we're doing it. So in this example, we're going to start our search from vertex C, and we have to do a little bit of setup to begin with. Vertex C first is going to get colored gray, and we're going to add it to this queue. And the queue represents verts that we have visited and we still have some work to do on. And so the first thing we want to do is identify C's neighbors. And so C has 2 neighbors that are still colored white, B and G. And so I'm going to draw a thicker line here to indicate that these are the neighbors that we're looking at. So C has 2 neighbors, B and G. We'll take the first neighbor B, and we'll color it gray, and we'll add it to the queue. And we will take the other neighbor G, and we will color it gray and add it to the queue. And then we have now successfully explored all of C's neighbors. So we're done with C. We're going to change its color to black and remove it from the queue. And we are now done with it. We're not done exploring yet. We know this because we still have items in the queue. So let's take a look at the next item in the queue. We'll look at it. We won't pull it off the queue yet, but we'll have a look at it. It's B, so let's look at B's neighbors. Same thing again. B has a neighbor in F, so I'm going to take F and color it gray, and we'll add F to the queue. E is another neighbor, so let's go ahead and color it gray and add it to the queue. as per usual. And A is another neighbor, so let's go ahead and color it gray and add it to the queue. And at this point, we've explored all of B's neighbors that are still colored white, and so we're done with B. Let's color it black and remove it from the queue. And that's that step. Same thing again. We are not done because we still have items in the queue, so let's look at the next item, G. Let's find all of G's neighbors that are still colored white, and we've got one of them over here at H. So we will color it gray and add it to the queue. And then we're done exploring G's neighbors that are still white. So we'll color it black to indicate we're done with G, and we'll remove it from the queue. Now look what we have so far. We started at C, and we've been moving across this graph from left to right in a nice, slow, deliberate way. So we're gonna, each step of the way, we're exploring nodes on the graph that are another step farther away from where we started. So we're deliberately going vertex by vertex outward, taking another step farther, until we finally get all the way across. So what's next? F is at the head of the queue, so let's look at F's neighbors that are still colored white and color them all gray. There aren't any, so we don't do anything for that step. It means we're done with F, so we go ahead and color it black and remove it. E is the same thing. E no longer has any neighbors that are still colored white, so we're done with that step. We color E black and we remove it from the queue. A, does A still have any neighbors that are colored white? A does, but I'm going to also point out one thing right here. As we're looking through A's neighbors, let's check the colors. A has B as a neighbor, that's black. A has H as a neighbor, that's gray, and A has white as a neighbor in D. So we know what to do with the white colored neighbor because we've been doing that the entire time. But if we happen to notice while we're looking through our neighbors that we have another gray one in here, that must mean that vertex H has been reached at an earlier time from a different direction in the graph. And because we know it's been reached at an earlier time from a different direction, we know there must be a cycle in this graph somewhere. Otherwise, it wouldn't have been reached yet. So the fact that as we were looking for the neighbors that were still colored white, we happened to find one that was colored gray, this means we've detected a cycle. And sure enough, we do have a cycle here, C, B, A, H, G, C. You can go around this thing forever. So by finding a gray neighbor when we were looking for the neighbors that were still colored white, this lets us know that we do have a cycle. But let's continue on here. So we're not going to follow that one, but we do have this last neighbor here. So I'm going to thicken this line, D. We're going to change the color of D to gray, and we're going to add it to the queue. And then we are done with A. So it gets colored black, and this is what we have left. We're still not done yet because we still have things in the queue. So let's look at H. All its neighbors that are still colored white, it doesn't have any, so that means we're done with H. I'm going to color it black, and we'll remove it from the queue. Same thing again, we look at D. All its neighbors that are still colored white, it doesn't have any, so we're done with it. We color it black, and we remove it from the queue. The queue is now empty. We have now successfully explored this component of the graph. Note that if there was another component out here somewhere, some other piece that was not connected, this component would not have been explored at all because we wouldn't have had any way to reach it. So breadth first search will only explore the component in question that's all connected. If there's another connected component somewhere else, it won't actually be found. The other thing I'd like to point out is what do we have here in terms of all these bold lines? Here's a line that's not bold, but in terms of all the bold lines, if I go ahead and, can I do this easily? No, I can't. I can't add an arrow to it. But imagine there are arrows on these lines. Ooh, actually, can I do weight 3 and just overwrite? Yeah, let's do this. So let's make these all directional. Just the bold ones I'm doing. And remember, the bold ones represent when we were exploring these, the bold ones were the ones we highlighted when we found neighbors that were still colored white. So if we look at what we have here, just the bold lines, suddenly we actually have a tree, right? Ignoring this thin line here between A and H. Remember, we did not explore that because H was already colored gray when we were looking for neighbors still colored white from A. We've got a tree here. It's called the breadth first tree. And we constructed this while we were exploring the breadth first graph. So one way to create a tree out of the graph that you have. So now what you should do is draw yourself some sample graphs and go ahead and make some cycles in them, make them as complicated as you'd like. And for practice, do the breadth first search algorithm on that graph and do it on a number of them just to get the practice. And then later on, we'll talk about other algorithms for doing searches across graphs and implement a few fun things in terms of pathfinding and breadth first search and detecting connected components. Talk to you next time.